Day 4 in the collector's series, EE4S, and I have it connected like I did on the first day when I did the power and energy demonstration. And we're going to take some more data. It's actually the same data we were looking at before. And I have the oscilloscope on the right and the watt meter on the left connected to take the data that I need for today. And I haven't even said what we're doing for today. I'm just so excited about being back in the lab, in the workshop, and then work with it that way. This scope actually has an interface, but I couldn't get it to work. It is not a new scope. It's about 10 years old, and I couldn't get that interface to work. So we'll work from the photograph, and that is fine. I am also going to write down the data. So I'm going to also capture the main screen, and I want this data. So this is the drill press, and I'm going to switch away from the red line, just something maybe is accurate to 4 digits. And it may be, it may not be. I could call it 121 volts. It doesn't matter for what I'm doing here. And the watts, very conveniently, when I last looked at it, said 200 watts, so I don't have to worry about significant digits on that. But again, you can't assume that the last digit is accurate. So rounding that number, now it's 198, rounding that off to 200 is still the correct thing to do, and make a note that you only have 2 significant digits there, which means that's all we have in any of them. I'll switch this over to amps, and I'll get that value to 2.07, so we'll call that 2.1 amps. I is equal to 2.1 amps. And that's all the data there is to take here. So I'm going to shut everything down, and we will start recording again and do some calculations with this and go through AC circuit analysis using this actual data from the machine. Let's do some work with that data that we took. There's the data. Drill press was running, no load, it was not drilling. Voltage was 121.2. Actually, that has units on it. I think we all know what they are, but let's be specific. Volts. Real power, 200 watts. Current, 2.1 amps. That's what we read from the watt meter. We're going to work with the oscilloscope output. And full disclosure, I had to turn everything back on and take a new picture of the oscilloscope screen. The one I had so much glare on it that it was very hard to see, and I knew I could do better than that. So here it is. How's that? That looks good. The first thing I'm going to do with this is write equations as well as I can for those two waveforms. You see a lot of digitization on there. The scope does not have a really high definition screen on it. So you see a lot of digitization on the waveforms. And by that I mean the stair step shape of those waveforms, which makes it a little more difficult to read off the screen, but we'll do the best we can, and we have that data from the watt meter to compare with in the end. So let's start with that. Let's look at the two waveforms. First of all, we have a waveform here that is channel A, and that is the voltage. The channel A oscilloscope setting The first thing we'll do with these two waveforms is write equations for them, time domain equations. We have two waveforms. The larger one is channel B, and that is voltage. The oscilloscope settings for channel B are 100 volts, so the B channel is 100 volts per division. Doesn't say that on there, but that's what it is, standard for oscilloscopes. So that means one division marked on the screen is 100 volts. That waveform looks fairly sinusoidal. You can see it more here than here, but both of them are flattened. So it's actually not a pure sinusoid. We're going to assume it is. That's how we're going to do phasors with it. It's flattened because we have a lot of DC loads, rectifier loads in this house. And rectifiers only draw current at the peak of the voltage waveform. So we have a lot of current flowing near the peak of the voltage waveform, not so much flowing the rest of the time. So you get a bigger voltage drop at the peak, and that flattens the sine wave. I teach a class, EE 898. It's a graduate level class. We're planning to move it to undergrad, though. It's electric power quality that deals with all those issues. Very important issues in electric distribution. We'll call that a sine wave. We're going to call them both sine waves, even phase shift away from 0 degrees. And I'll tell you to start, we're going to use voltage as reference. Very common, again, in AC analysis, although not universal, but that's what I'm going to do here. So the phase angle for the voltage will be 0 degrees. Is it showing at 0 degrees? No. There's the peak, there's 0 degrees, but I'm calling it 0 degrees. I can call anything I want 0 degrees. I just have to make the rest of the waveforms relative to that. So now I have an equation, Vm cosine omega t. Phase angle on the current will be relative to the voltage. What's Vm? Peak value of the sine wave should be equal, positive, negative. What's the peak value? Here's 0. There's the peak value. We find the number of divisions and we multiply it by 100 volts. I'm going to call that 7 divisions. Sorry, not 7, 1.7 divisions. So that gives me, this needs to stop moving around. Vm is 1.7 times 100 volts, or 170 volts. Fine. We need omega. Omega is the radian frequency of the waveform. How do we find the frequency of a waveform? We measure one period of the waveform. There's a zero crossing. The waveform is going negative, so there's a negative going zero crossing. There's the next zero crossing, but that's positive going, so that's only a half cycle. There's the next negative going zero crossing, so I need to know the time period that is there. And I'm going to call that, here's 1, 2, 3 divisions, and I'm going to call that 3.4 divisions. So I'm going to say period T 3.4 divisions, so 3.4 times, what's the time base for the oscilloscope? 5 milliseconds. 5 milliseconds per division for time domain. So V of t is 170 cosine 370t volts with t in seconds. That's important to have that in there. You have to say what t is. If it's milliseconds, it'll be a very different equation. So I know that t is in seconds because the radian frequency is given in radians per second. That's the voltage equation. Now we need the current equation. This plot is pretty drawn up already, pretty messed up already, so I just copied it again. It's the same one. Put it below so we can calculate the current equation here. Channel A is the current, I of t. Not sinusoidal. Almost a triangular wave. Didn't look quite this way the first time we did it a few days ago for the day one. I'm the only one who got to look at it. It was closer to sinusoidal. I don't know why it is shaped this way. It is an induction motor that is running unloaded, and an unloaded induction motor can draw a fairly strange sine wave. It's possible that the voltage is higher. Yesterday when I actually did these, when I took those measurements, voltage may have been higher than the other day, and the motor actually may be getting close to saturation, which distorts the current waveform. That's my best guess on what's going on there. We're going to once again call it a sine wave. So my current equation, I of t, will be I magnitude cosine omega t plus or minus theta. We'll have to figure that out. So let's start with the current magnitude. Current is channel A, 50 millivolts per division. There's the peak value. There's a peak value that we can look at. So we need that distance right there as divisions to get the peak current. So I'm going to call that 0.6 divisions. I've already done the calculations. I'm pausing to look at my notes. 0.6 divisions. So the current magnitude is 0.6 times 50 millivolts. And that, I do not have to look at my notes, is 30 millivolts. Well, that's interesting because I'm looking at a current. I would expect units of amps on that current. And I'm getting units of volts. There's a clamp-on current transformer in that circuit. There it is, shown in the circuit, this device right here. Circuit is turned off. I'm going to disconnect it. It was clamped onto one of the wires supplying the drill press, and that's the clamp-on current transformer that plugs into the oscilloscope. This is a nice current transformer because it converts the current to a voltage. And there is a switch right here. You can see the switch. You're not going to be able to see the markings on it, but I can tell you what the markings say. They give the conversion for the current transformer, and the setting that it's on is 10 millivolts per amp. The other possible setting is 1 millivolt per amp. That's for higher current values. So we're set on 10 millivolts per amp. So that's what we'll use for calculating the current. So let's go back and use that to calculate the current. Current transformer. And you'll hear that referred to as a clamp-on CT. 10 millivolts per amp. So to get, this is not IM. IM is 30 millivolts, and we'll need to divide by 10 millivolts per amp. So that gives me 3. I can call it 3.0 amps. Take credit for 2. No, I can't. No, I can't. I have one significant digit there. Forget the 3.0. I have one significant digit on this. And that's because that's as close as I can read. Don't claim 3.0, 3.03. You can't read this. You can't read that screen any more than 0.1 division. And even that is questionable. So 3 amps. Phase angle. Phase angle. Oh, goodness. Okay. What's phase angle? We need to get the time period between either peak values or zero crossings. And we have a nice zero. We have several zero crossings on there. And we need to just get an estimate for what one of those is. So there's one here, but it's hard to pick out there. We'll call it like that. There's another one here that looks like about like that. And there's a third one here. So we can use any of those as the distance between the two waveforms, and that's what will give us the phase angle. So I'm going to call it 0.3 divisions. So delta t separating the waveforms, 0.3 divisions times 5 milliseconds. .5 milliseconds. Is that what we want in this equation? What units do we need in that equation? Let's scroll down and think about that. It says omega t plus theta. This is what we commonly use as engineers, omega t plus theta. So what are the units on theta? Is it time? It's a time domain equation, but this is radians per second times seconds, time in seconds, so radians. So theta needs to be in radians. All right, we need to convert 1.5 milliseconds to radians. Well, how do I do that? Go back to the plot. We got to figure out how to label this thing in radians. Okay, how do we do that? Let's go from here. There's a negative going zero crossing on phase A. I am assuming, by the way, that these are both the same frequency, and physically that's the only thing that makes sense because it's the voltage and current in the same circuit. There are no active components in there that could change the frequency. So frequency is the same. So I'm going with the same omega equals 370 radians per second. Should have said that earlier or later. I interjected it there, but 370 radians per second. So I don't have to calculate that again. I do need to know this. Well, that's the period. I already calculated the period up here, and the period was 17 milliseconds. So I know that. 17 milliseconds, but it's a sine wave. If I want to call it radians or degrees, how many radians or degrees is that? It's one cycle. One cycle is 360 degrees. That's how we define it, or 2 pi radians. So 360 degrees, 2 pi radians. Radians is actually unitless. Don't ask me why. Ask a math person why. But 2 pi radians, we usually put the units on it so we know what they are. All right, so I have 1.5 milliseconds out of a 17 millisecond cycle. Stop moving. 1.5 milliseconds out of a 17 millisecond cycle. There's a ratio, units cancel, and that's equal to 2 pi radians or 360 degrees, and that gives me an angle of 0. All right, I'm going to give you more significant digits than I can actually take credit for. I'm going to take 0.55, just so we're not being so inaccurate. I can't claim that I know those. I should round that off to 0.5 or 0.6, but for my calculations, I'm going to leave it there. And then if I need to give this to someone, I'm going to take it down to one significant digit. 0.55 radians, or 1.5 over 17 times 360 degrees is 32 degrees. We usually label these things in degrees as engineers, not radians. I have a better feel for 32 degrees. It's about a tenth of a cycle than 0.55 radians, which is also about a tenth of a cycle. But as far as being able to just think about it, degrees works better for me. So that's why we do it. What else do we need? We need one more thing. I should have just put plus or minus. It's actually plus theta, and theta may be negative. We need to know if it's positive or negative. Which one of those waveforms is leading? This is waveform B. This is waveform A. For some reason, I always wanted to say that the one that is farther to the right is leading. I'm not sure why. Something in the way I learn things. But it's the first one to get to a point. So we have a peak. Let's look at that peak where I labeled it. There's a peak, and it's a peak after the waveform was rising. Here's a peak for channel A, peak after the waveform was rising. Channel B got to that peak before channel A, which means B leads A. Which means B has a more positive phase angle than A. Voltage has a more positive phase angle than current. So current I of T is equal to current magnitude. What was it? Three amps. Cosine. You can write these as sine. Standard is cosine. But if you write one of them as sine, you have to write all of them as sine. That's all. When we go to phasors, it won't matter. It'll give the same result. But cosine is the standard. That's why we use it. Omega 370t minus 32 degrees because current lags voltage. If you remember anything about power factor and loads and all that, it's an induction motor. Current always lags voltage in an induction motor unless someone has put a capacitor on it that's hidden, and that has happened to me more than once out in the field looking for power factor, looking at power factor in an industrial site, and it turns out their power factor is leading. And so we have to go out in the plant and find all the capacitors that have been stuck on induction motors, which is very common. So even though it's an induction motor, you really need to look at which way the angle is. Okay, that's the current angle. There's homework 4, but we're not ready for that yet. I need space. Give me space here. I could have deleted it and re-pasted it lower. That would have been easier. Okay. Well, I'm through with the oscilloscope plots. So we'll change colors to signify that. We'll go back to blue. We can work with those time domain equations, and we can do anything we want with those time domain equations. But if we do, one way or another, to analyze an AC circuit, we have to solve differential equations. So we can apply a sinusoidal voltage source to resistor, inductor, capacitor combination, and we can calculate the current. We can define the voltage as a time domain equation, and we can calculate the current as a time domain equation. we have to solve differential equations because in an inductor, L di dt, in a capacitor, I c dv dt, we can set up a system of equations, time domain, differential equations, and solve the differential equations. And you can actually now, you can put those in MathCAD, MATLAB, Mathematica, any of that math software will solve those differential equations for you. Those software packages are wonderful, and you need to learn to use them sooner or later. But so we're going to solve differential equations, whether you like it or not. But there's a really nice technique for solving differential equations. This is important. You may not have heard this before unless you took 282 with me. Solve differential equations that are single frequency sinusoids. This only works directly if you only have sources that are single frequency. If you have sources that are multiple frequencies, which is not uncommon, you can still use superposition and this technique, and it's better than writing the time domain equations and solving the differential equations. But we're going to be looking at single frequency sinusoids. That's the whole AC grid. It's a single frequency sinusoidal grid. It's all synchronized, so this works. Single frequency sinusoidal equations, and the technique is called phasors. We'll write the phasors for those two voltages. The voltage phasor, V, is, where's the time domain? There's the time domain current. Let's write that first. It's right there. Let's do it. I, put a bar under it, indicates it's a vector. Magnitude 3, hang on, let's go verify this against the data that we took for that drill press. We got 2.1. The scope gave us this. IM equals 3. I keep wanting to put that 0.0 on there. 3 amps. Why are they different? Because this is RMS. The RMS value of a sinusoid is peak value over square root of 2. What's that? Wow, 2.1. I read that nicely. Okay. Doesn't look like we have an error there. Convention in AC circuits is to use RMS values. We'll talk more about that when we get into power. RMS values are equivalent to DC values. They give you power directly. So, where were we? I is equal to 2.1. Angle. We just need an angle. Phase angle, minus 32 degrees. This value does not need the frequency in it because there's only one frequency. Voltage. Now voltage was, go back up to the voltage. Voltage was 170. Let's go up and calculate. V equals 170. VRMS is 170 volts over square root of 2, which gives me 120. Pretty close. Which one would I trust? I'd trust the watt meter because reading off that scope is, it's It's difficult to read. So we'll call it 120 volts, or we could call it 121 because that's what the watt meter gave us. Today it doesn't matter. 120 cosine. No. We're doing phasors. That's RMS. This is RMS. I know in circuits 1, 282, you almost certainly used the peak magnitude in your phasors, but that's not how it's done in reality. So 120 cosine omega t, we called that the reference angle, so reference angle is 0. There are, I keep putting that cosine in, sorry, I just can't quit. Angle, 0 degrees, reference is 0 degrees. 120 angle, 0 degrees. I should edit that out, but this is how my real classes go, so I'll leave it in. Well, there they are. They're the phasors. What can I do with that? What can I do with it? I can calculate impedance. I can derive a circuit model for that induction motor. Z equals V over I. 120 volts, angle 0. I didn't put units on these. I got counted off regularly in circuits 1 for not putting units on my correct answers. I thought that instructor would know what the units on voltage and current were. When I do that math, I don't have this in my notes, 120, here's how it works, 120 volts over 2.1 amps is the magnitude. Angle is 0 degrees minus 32 degrees. So I just need to quickly do 120. This is also how my classes go. You're getting something close to the real experience today. 57 at an angle of minus 32 degrees ohms. That's the impedance. What I have in my notes is what we more commonly use for impedance. We split it into real and imaginary, so it's 48 plus 30. 48 plus J 30 ohms. That could be my model for that induction motor. There's homework 4 again. I'm not ready for you. Please go away. In fact, I'm going to discuss homework 4 in a separate video. Just disappear. Thank you. 48 plus J 30. So I could say, here's my voltage source, which I said was 120 volts. And here is a model. This is not my motor, but here's a model of my motor. 48 ohm resistor. Sorry, my resistors and inductors look a lot alike. J30 ohm reactor. This is an inductor. X of an inductor, which is 30 ohms, is omega L. X is actually a scalar value. You put the J in front of it and when it's impedance. So L is 30 ohms over 370 radians per second. And when I do the math on that, I get 81 millihenries. Ohms divided by radians per second is henries. 81 millihenries, that's L. So there's a resistor, there's an inductor. That's my circuit model. When we get to induction motors, we're going to develop a circuit model of an induction motor, and we'll come back to this motor and we will see if that's a good model. It actually is not a great model, but for now, we can say that's the best model we have. That's phasor analysis. Next, I will take a look at homework 4, but I'm going to do that separately because it kept getting in my way and I was tired of it. We'll take a look at homework 4. It's going to give you some practice on phasor analysis.